So in today's video, we're going to talk a little bit about vertical tangents and normals. So we actually briefly touched on this in a previous video, but today we're going to kind of just continue with this example, which is the semi-unit circle example, which I've graphed out over here. And I'm going to talk a little bit about vertical tangents and normals a little bit more in depth. And so let's actually go ahead and do that. So we've covered the equation of a tangent line. We know that a tangent line will have the form y equals dy dx times x plus b. And, of course, this is in the slope-intercept form. And we also know that the normal to a graph will be -1, or will have the form -1 over dy dx times x plus b. So this one right over here would be a tangent, and we said that this one over here would be a normal. And so what happens when we have a horizontal tangent? What does that mean with respect to the normal? So let's actually go ahead and kind of look on this graph and determine where we would have a horizontal tangent. So the most obvious point is this one right over here at x equals 0. It looks like if we were to kind of approximate the tangent line, it would maybe look something like this. It would just be kind of this sort of horizontal line going through x equals 1. And if we wanted to actually prove that, so here we have the derivative f prime of x, and we got this one in the previous video when we actually used this example. And in order to actually determine the equation of the tangent line at this point, we can go ahead and just input f prime of 0, because we know that that's going to be the slope of our tangent line at x equals 0. And so we know that f prime of 0 will just be -0 over the square root of 1 minus 0 squared, which is just 1. And so this is going to be equal to 0. Oh, God, what just happened? Okay, I don't know what's going on, sorry. So this is just going to be equal to 0. So we know that the slope of the tangent line is going to be equal to 0. And so that tells us that this term over here, this dy by dx term, is just going to go straight to 0. So we're going to have y equals b as the equation of our tangent. And we know that our y-intercept over here is just +1. And so we'll get that y equals 1 is the tangent. So actually, let me write this over here, y equals 1. But then what does that mean in terms of the normal? Well, we know that the normal is going to have a slope of -1 over dy by dx. And so if in this case, if the derivative is equal to 0, then we're going to just have -1 over 0 as the slope of our normal line. And that doesn't necessarily work out. And so instead, we know that our normal is going to have the form x equals some constant a. Right? And how do we know that? Well, because if we were to just look graphically, we see that we have a horizontal tangent. So then if we were to kind of approximate the normal, we know that the normal has to be perpendicular to the tangent line. So if we were to approximate the normal, it may look something like this, right? It would just be this sort of, this sort of vertical line going straight up. And we know that this vertical line exists on the on the y-axis, so it's going to be x equals 0, right? It's just going to pass through it's just going to be right on top of the y-axis, we could say. And so that right over there would be the case in which we have a horizontal tangent and as a result a vertical normal. But now let's go ahead and see what happens when we have a vertical normal, or a vertical tangent and a horizontal normal. So if we were to look at this point over here, x equals +1, we're kind of going to approximate the tangent line. We can go ahead and do that. We may get something like this. Now, we're going to discuss the kind of conditions for actually having differentiability at a point. And we would find that this point wouldn't really be differentiable because it's not continuous, but we're just going to assume that it is for the time being, just for the sake of the example. Let's assume that this function is continuous, that it goes off like that, whatever. And so at this point, our tangent would be vertical, right? Because we can even go ahead and try to prove that ourselves. We know that f prime of 1 is just going to be equal to -1 over the square root of 1 minus 1 squared, which is just going to be -1 over 0. And so this would tell us that we kind of have, an infinite slope, whatever. And so this would indicate that we have a vertical tangent or vertical line. And so then we know that the normal is going to be a horizontal line. So let me actually just erase this part because we'll talk about differentiability a bit later on. And so if we have a vertical tangent, then we know that our normal is going to be horizontal, right? Because we have to be perpendicular to our tangent line. And so what would the equation of our tangent line be over here? Well, we know it's going to be x equals some constant, and it passes through x equals 1, so the equation of our tangent is going to be x equals 1, and it's a vertical tangent. And then our normal, we know that our normal is a horizontal line, and it has to pass through the x-axis, and so we know that this is just going to be y equals 0, right? And so the point is that whenever we have a vertical tangent, then ideally we would have a horizontal normal, in general at least. And whenever we have a vertical normal, then ideally we would have a horizontal tangent. You just have to think about that in terms of the fact that the tangent and the normal have to be perpendicular to each other.